In this video, we're going to talk about piecewise defined functions. A piecewise defined function is a function defined in terms of pieces. So I've drawn two examples of piecewise defined functions. Now, on the right is how you'd write a piecewise defined function out. So f of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. Notice this is two different pieces, and by definition, this is the absolute value function. So piecewise functions are either continuous or discontinuous. A continuous function is a function where there are no holes or jumps. Absolute value function is an example of a continuous function. Remember, it's V-shaped. There's no holes. There's no gaps. That's a continuous function. Discontinuous is a function where there are holes or jumps. The first two pictures I've drawn are examples of discontinuous functions, but they're only discontinuous at certain domain values. If I can get rid of those discontinuities, the rest of the function would then be continuous. So any points where holes or jumps occur are what are called points of discontinuity. I'm going to use x coordinates to identify points of discontinuity. So for instance, notice on the left, the domain value of x equal to 2 is a point of discontinuity. If that domain value of x equal to 2 is gone, the rest of this function is continuous because I would have no more jumps or gaps. The example on the right, x equal to 4, that's the domain value, is a point of discontinuity. If I was able to color in that hole, the rest of the graph would be continuous. So now that we've taken a look at piecewise defined functions and points of discontinuity, I'd like to be able to graph the following piecewise functions. Okay. Then we're going to determine the domain and the range of the function, and then identify points of discontinuity. Now, notice here, when I look at this piecewise defined function, it has three different functions. One is f of x equal to -1. Notice the domain. That is from -infinity to -1. Second one I'm going to do in blue is f of x is equal to -2x. Its domain, I'm going to write above, is from -1, I can include, to 2, which I cannot. And the third one I'll do in red is f of x equal to x. And notice that domain, that's from 2, which I can include, to infinity. Now, I want to pick 3 points for it, but I have to be careful about the domain restrictions for every piece of this piecewise defined function. So let's start with f of x is equal to -1. So I'm going to write this as x and f of x. Now, I know -1 is not in the domain, but this is what is called a boundary value, meaning the graph is not going to go any farther to the right than the domain value of x equal to -1. So I want to include that. When I plug in -1 into the function, I get -1. That is an open circle because -1 in the x is not in the domain of this piecewise function. But what is a domain value that is? Okay. Well, -2 is. When I plug in -2 into this function, I get -1. Because -2 is in the domain of this piecewise defined function, that's a closed circle. What other domain value? Well, -3. Because -3, again, is in this domain, it's going to be a closed circle. Now, I'm going to put an arrow to remind me, because the domain is -infinity, part of this graph is going to go on forever. All right, now let's do f of x is equal to -2x. So create table. Okay, so let's start with then 2. Now again, 2 is not in this domain, but it is a boundary value. So when I plug in 2 in the function, I get -4. 2 is not in the domain, open circle. Well, what else? 1 Plug it in, you get negative 2. 1 is in the domain, that's a closed circle. Well, what else? 0. That's 0. 0 is in the domain. And negative 1. Now, negative 1 is in the domain, that's a closed circle. Notice you have a beginning and an end, so there will be no arrows here. All right, let's do the red then. All right, so what do I want to do here? I want to plug in 2. 2 is in the domain and it's a boundary value. Plugging that in, you get 2. Well, what other value is in the domain for this function? Well, 3 is. So is 4. Now, because it's going to infinity, I need an arrow to remind myself that part of this function is going to go on forever. Okay, so now what I want to do is graph these 3 pieces. So let's go down, and I'm going to start with the black. So notice I have changed it from y to f of x, and I've labeled my slashes. All right, so in black, let's do this. So negative 1, negative 1. Oop, got to change that to black. So negative 2, negative 1, and negative 3, negative 1. Goes on forever because it's negative infinity to the left. Now, let's do the blue. 2 and negative 4. In fact, I got to scroll down so we can do this. And let's see, that's an open circle. So what else? We've got 1 and negative 2. We've got 0, 0, and negative 1, 2. And connect. Now, let's do the graph in red. That's 2, 2, and 3, 3, and 4, 4. Now remember, it's going to positive infinity. So it's going to have an arrow going forever to the right. So here's my graph of this piecewise defined function. Now, let's determine the domain of the entire function that we just graphed. Well, every time I see a hole for the domain, it's colored in somewhere else. This hole is covered by this point in blue for the first hole in the domain. This hole in the domain is covered by that red piece. So the domain is going to be negative infinity to positive infinity. The range, okay, that's the y or f of x values. Well, start from the very bottom. We go to here. Again, there it's 1, 2, 3, negative 4. Now, it's an open circle, so negative 4 is not included. Go up. Now, this hole here, every single one of these values has the same range value as this hole, which is negative 1. And it's connected the rest of the way. No holes or jumps or gaps to worry about. That goes to infinity. So, my points of discontinuity. Well, one of them is at x equal to negative 1 because of this hole and this jump and gap. Where else? Well, that's x equal to 2. So those are my points of discontinuity. But remember, when I write the points of discontinuity, I only want to refer to the domain values. Okay, one other one I want to graph. Again, this particular function has 3 different pieces, so let's separate them first. So g of x equal to 1 minus x. Now, x is less than 0, so that's negative infinity to 0. In blue, g of x is equal to x squared, and that domain is 0 included to 1. 1 is not included, that's a 1. And in red, I have g of x is equal to the square root of x, and that's 1 to infinity. All right, so let's create a table for this. But remember, you need to keep track of where what your domain for each particular piece is going to be. For the first one, even though 0 is not part of the domain, that is a boundary value. This lets me know where to stop the graph on the right-hand side. Plugging in 0, you get 1. 0 is not in the domain, so that is an open circle. So what is -1? Well, plug in, you get negative. You get +2. -1 is in that domain. That's a closed circle. -2. That's 3. Again, -2 is in this domain. That's a closed circle. Draw me an arrow to remind me that it's going to go on forever in one direction. Okay, in blue. So that's going to be x and g of x. So plugging in 0, that's 0. Now remember, 0 is in the domain, so that's a closed circle. Now, I want to pick something that is in between 0 and 1. Best suggestion might be 1/2. 1/2 squared is 1/4. 1/2 is in the domain, so that is going to be a closed circle. And then I'm going to pick 1. 1 squared is 1. 1 is not in the domain here. That is an open circle. Okay, let's go in red then. Okay, all right, I'm going to start with 1. 1 is a boundary value, but 1 is included here. So the square root of 1, 1. I'm going to pick easy values. 4, square root of 4 is 2. So closed circle, and then the square root of 9 is 3. I will draw an arrow because I know in one of the directions that piecewise function is going to go on forever. Okay, so now let's graph these three. Okay. A couple of comments. One, I'm going to change this y to a g of x. And I'll put my 1 here. All right, so let me graph the black first. So that's going to be what? 0, 1. And that's an open circle. And what? -1 and 2. And -2 and 3. So it's going to go on forever to the left. Now, let's do the blue. So 0, 0. 1/2 and 1/4, that's about there. And then 1, 1. That's an open circle at 1, 1. And remember, because, let me scroll back up, this is a quadratic function, you would expect this to be curved. Okay, not a straight line because it's not a linear function, it's quadratic. Okay, let's graph the last one, then I'll do that in red. Now notice, for this piecewise function, 1, 1 is now closed. So I'm going to close this in red, and I'll do 4, 2, and 9, 3. All right, so the domain for this entire function, well, the low spot is 0, and that's included. There's only one hole for the domain, which is at 0, but that's covered. So 0 to infinity. Okay, the range. Again, smallest range value is at 0 because it is a closed circle. That's included. The only hole for the range is 1, but it's colored in thanks to the red. There's no other jumps or gaps to be concerned about. That's also 0 to infinity. Points of discontinuity. I'm going to abbreviate. Here, where are there holes, jumps, or gaps? X equal to 0. Now, notice x equal to 1. Thanks to the red graph, that 1, 1 is closed. So x equal to 1 is not a point of discontinuity. So your only point of discontinuity in this graph is x equal to 0.